Thank you very much, Bea, for the introduction. Thank you very much, everyone. Also for the invitation to all organizers. First time in Toronto, I'm very happy to be here. Yeah, so this subject of bus martingales, with my collaborators, we have been working on this for a while. So I thought I would give an overview, and there are also some open questions. I think some of you have seen these talks given by me or my collaborators over these years, so I apologize if there's any repetition. So the plan is to talk a little bit about martingale optimal transport, because this has not yet been covered in the workshop. Then explain to you what are these bus martingales, their optimality properties, and then finally some slides about maybe how you could find them or compute them. Okay, the talk is based on these works with friends and collaborators. I will tell you, which results comes from which paper. So to this audience, I don't need to introduce classical OT. I will just use this notation, capital Pi, for the set of couplings with the given marginals. And I only make the comment that, when you're transporting from RD to RD, probably the best studied case, as you know, is a quadratic case. I'll say that once. So martingale OT, okay? So, and throughout the talk, we're working on RD. So from RD to RD. And yeah, I should say, what is a martingale? So a two-step martingale, yeah, it's simply, let's say, a coupling. For us, it will always be mu to nu. We think of mu as something happening, let's say, at time 0, and nu as something happening at time 1. So we consider like a time direction. And the martingale condition is written here. So it simply means that, yeah, x denoting always what happens at time 0, so distributed like mu, and y denoted what happens at time 1, so distributed like mu, is this constraint on the conditional expectation. So where you're going to move, given where you are, your best estimate for that is where you currently are. Okay. I will also be using this notation here. So if pi is a coupling, with the marginals mu and nu, then I can decompose it as, what happens to the first marginal, and then conditional on that value, what happens to the second variable. So yeah, if you don't like so much the notation of improbability, then the martingale condition is just written like this. And I will be denoting by capital pi m the set of martingale couplings with these marginals. Okay, so a subset of the original set capital Pi. If you would have more time steps, including, for instance, a continuum of them, the martingale property just means you take 2 time points, and between these 2 time points, you have exactly this identity. Okay. Good. So the martingale OT problem is looks exactly like the OT classical OT problem, but you add the martingale constraint. Okay. And here I'm highlighting 3 differences to classical OT. One difference is that the set of martingale couplings with the marginals mu nu could be empty. As you can see from here, martingales have this tendency that they will become more and more dispersed over time. So clearly, for instance, if nu is more concentrated than mu, there couldn't be a martingale from mu to nu. So you need a condition for that, and that's expressed in Strassen's theorem, giving you the precise conditions. Yeah. And throughout the talk, then, I will always assume that mu and nu are in this convex order, so we're not optimizing over the empty set. In OT, the product coupling is always feasible. Here, this is not the case. Second thing, in OT, it's very important to study deterministic couplings. So when y is a function of x, let's say, Monge couplings. Well, for martingales, being deterministic, it means being constant. Yeah? Because this condition is saying that on average, you don't move when you go from time 0 to time 1. So if you're deterministic, then you have to stay put. So it doesn't make sense to study Monge couplings in the setting of martingales. And a third big difference is that the emblematic quadratic cost for OT would lead to a trivial problem in the setting of martingale transports. And the reason is that when you develop the squares and you have the inner product of x and y, you would apply this condition, the so-called tower property if you want, or just using the disintegration, and the expected value of the inner product would be x squared integrated. So then all martingale couplings would have the same objective function value. They are all simultaneously optimal in that case. Okay. So the nature of martingale OT is quite different than classical OT. That's what I wanted to emphasize. And I also want to motivate where does this problem come from. So it's coming from math finance and also model calibration in math finance. Here is an incomplete list of people who have worked on the field. So this is how the problem actually appeared. So S is a model of a financial asset, the price of a financial asset. You assume that you can retrieve the marginal distribution of S from, let's say you go to Yahoo Finance and do your homework, and then you manage to do that. I will not go into details. But you want to find the value of what's called a financial option that depends on the joint behavior of the market, not just on the marginal. And so what the theory tells you is that the fair price of this financial object lies between the inf and the sup of all these integrals as you look at all possible martingales compatible with the data. So that's how the problem appeared so option pricing model free. Another instance is calibration in math finance. This gives me a bit the chance to talk about continuous time, but I will make this more precise later. So, the relevant quantity for a continuous martingale is its instantaneous volatility. So essentially, how much it varies in a small time interval. That's what I'm denoting by capital sigma. And now you could imagine a loss function that depends on the value of the martingale, maybe time, and its instantaneous variability. And you could want to minimize that, for instance, to calibrate it. Yeah. In that case, this set, I will not change the notation. This set denotes continuous time martingales starting in mu, finishing in mu. And when you minimize this problem, you possibly identify, it's like calibrating to data your martingale model of the market. So discrete time, continuous time, both interesting stuff in martingale transport. And okay, so this is how we started our research program. So very central to OT is what's written here on the slide. So here is the quadratic case of classical OT. And as you know, it is entirely equivalent to this time-dependent variance. Yes. So I like personally the one at the bottom. So you're trying to go from mu to nu. Your particles admit a velocity, and you try to find the curve, the random curve that does this with the least energy. And as you know, there's complete equivalence here. So if you have an optimizer here, then your B is just the y minus x under that coupling. So it's a constant velocity. Okay. One way to think about this, which is maybe not so usual to do so, is that imagine that I call omega a constant speed particle, or for instance, a constant curve, just the curve that stays, let's say, at 0, and that's it. And I want to sort of take that as some sort of reference that I'm trying to project on the space of processes that start in mu, finish in nu, and that admit a velocity. Then the solution to this projection problem would be the same as the solution to this problem. Yeah. If I specify to you correctly what is this distance, maybe this suggests that this could be done with a causal transport-based setting. But yeah, that's a bit the interpretation that we have in mind. And the reason is that this interpretation can be adapted to the case of martingales. Yeah, so we're trying to think what could be an analog of this slide in the case of martingales, and this interpretation is helping us because you could say, well, instead of finding the process which is closest to the constant speed particle, but with the given marginals, maybe I want to find the martingale who is closest to, and I need to tell you what. So yeah, the canonical martingale in continuous time would be Brownian motion, would be the analog of the constant speed particle because it's the constant volatility martingale. So you might want to do this. So project your Brownian motion onto the set of martingales that meet the data. Yeah. Again, I will need to specify what does it mean, what is the cost. Yeah. But seen in this way, then I think it's clear that we're trying to answer the same question as above, but in this case of martingales. And now let's make it concrete. So if you come from stochastic analysis and I'm telling you you need to compare a martingale M and the Brownian motion B, then your immediate response would be, yeah, to compare them, let's use the Hilbertian approach. So we just take the quadratic variation of the difference as the cost criterion. Yeah. So if you're not familiar with that, this is like the right way to measure the size of a martingale. Here is written what this is. It's essentially collecting the increment squares of this object as you go finer and finer along a partition. And that turns out to be the right way to measure the size of a martingale. And finally, using tools from stochastic analysis, you come to the formulation that that is analog to the optimal transport case. So here's a bunch of information actually. So so in the OT case, I said that the particles admit a velocity field. I called it B in this formulation or V in this other formulation. Martingales don't admit a velocity field. Yeah, but you can look at how much they vary in a small time interval, and that's what we usually call sigma square. So this sigma square is how much the martingale varies in a small time interval, let's say. And Brownian motion is a martingale that has that varies in a constant way at a constant rate. I don't know how to say it, in every small interval, let's say rate 1. And so the problem that we write here is you compare for a martingale M its volatility coefficient sigma to the one of Brownian motion, the identity. Yeah? And you want to minimize this quantity. So this is the dynamic problem that will accompany us in the lecture, in the talk. Yeah, so we're comparing Brownian motion to the martingale that fits the data, period. And this is the way we do it. So quite similar to this slide, but here we're comparing to the identity. And here it's not of this form. Your martingale is sigma times Brownian motion. You may wonder, okay, but what about the static formulation? So maybe in retrospect, it's not so difficult to see that. So this is trying to say how far you are as a continuous time martingale to Brownian motion. Then you could ask, if I am just in 2 time periods, what does it mean to be close to a Gaussian? Would be the replacement of this or the analog of this. And that turns out to be an interesting static problem or 1 period problem. So among your 1 period martingales, try to find the one that's on average closest to Gaussian. Yeah. What we really do is compare the conditional distributions to the ones to properly centered Gaussian. Now this is a weak transport problem. in the sense of Gosselin and co-authors, but it's sort of static, or one period would be correct to say, and this is continuous time. Okay. So the first result that we got that already showed that we were after maybe an interesting object was that we could show that there are unique optimizers to these problems, and these problems have the same value. And if I tell you an optimizer in one problem, I can tell you who is the optimizer in the other problem, and vice versa. Okay. To see that this one has a unique optimizer might be surprising to some people, because, for instance, the mu and nu could be purely atomic. But the magic is that you're comparing in this expectation to the Gaussian. So then this integrand is strictly convex, and this is the kind of stuff that would give you uniqueness. It's less clear why you would have uniqueness above, but yeah, trust me. So in our first paper, we were able to show that, and a bunch of other properties. Important martingales like Brownian motion, geometric Brownian motion are optimal. And we could really characterize optimality of a martingale in dimension 1, but it was left open what would happen, how, if you could really understand this in higher dimensions. Yeah. So I should also say that what we do is follow always the probabilistic perspective, but you can also do this with an analyst's perspective, like in this paper, or also what Grégoire Lepere has done in several papers with co-authors. You could translate everything in terms of PDEs. Okay. So let's start to talk about optimality. How does it look? How does an optimal martingale look, for our problem? So what I'm giving you here is the case where the initial distribution is a Dirac, and the other one has the same mean. So then they would be in this convex order. And we define the martingale M star like this. So at time 1, we just take an increasing function of the Brownian motion at time 1. And the increasing function is chosen such that it would put the standard, push forward the standard Gaussian into nu. This tells you what happens at time 1. If you want to see what happens before time 1, you just take conditional expectations. This defines continuous time martingale. And it turns out to be optimal between these marginals. So essentially, when your mu is a Dirac, we already know who is the optimizer, and these guys are called Bass martingales, classically. So we now try to generalize this. We want to allow, non-trivial initial distributions, and for that reason, we also need to generalize what does it mean to be a mass martingale. So the definition that we took, I don't think it was out there before, is very much the same. First of all, easy to generalize to higher dimensions. Instead of f being increasing, I just take f to be the gradients of a convex function. And but my Brownian motion, I allow it to start possibly with a non-trivial initial distribution. Okay. So then when I define MT by conditional expectations like this, you can use, it's not difficult to tell who is this function exactly of t and Brownian motion at time t. And at time 0, this M would have a non-trivial initial distribution because B0 has. Okay. Okay. So here's just a picture to give you a feeling. So mu Dirac, nu Bernoulli. This is how the Bass martingale would look like. A few paths, you can see that it does end in a Bernoulli on only +1 or 0, and here are a bunch of paths. All right, so to understand, we want to characterize the optimizers to our problems. We hope that they have to do with Bass martingales, but this is the case when mu is a Dirac. It turns out that it's not so easy to do that, so we need an extra condition, but I will come back to this. It's a sort of mixing, or what I wrote here, connectivity condition, that in classical OT, this would be easy to prove with the product coupling. So if I have two sets that are charged, then I can find a coupling that charges their product. I would just take the product coupling. But it's non-trivial to say that there is a martingale going from one set to the other set with positive probability. Okay, it's at the moment just an assumption, technical. And yeah, in the work with Matthias, Walter Schachenmeier, and Bertram Chidera, we obtained this result. So for a feasible martingale, it's equivalent to be optimal and to be a Bass martingale. Okay. So in the case of when this assumption holds, then optimality, which is is a soft condition, is equivalent to some sort of very structural condition, like being a Bass martingale. And the power of the theorem is not really the equivalence, but just the fact that under an assumption like the one above, because an optimal M always exists from soft compactness arguments, it follows that a Bass martingale exists between mu and nu. So from the assumption above, it follows that the Bass martingale exists between mu and nu. And this is, I think, a strong statement. As I'll try to explain now. So, so this is what does it mean? So we have here a distribution alpha, and the Brownian motion started like alpha. It moves around times 0, and at time 1, it has, of course, the distribution alpha convoluted with the Gaussian. I will use this a lot, alpha convolution with the standard Gaussian. Well, what does it mean to be a Bass martingale? It means here I apply the gradient of a convex function. Let me call that psi star. Now this star means convex conjugate. It will come in a moment why. But the gradient of a convex function, it sends me to what I call M1. This is distributed like mu. And in fact, if I give you alpha, you can always find by Brenner's theorem such an F that would take this absolutely continuous measure to nu. But now you sort of propagate backwards in time this. So MT would be the conditional expectations of this one, given the information up to time t. So at time 0, you get F convoluted with the Gaussian evaluated on the Brownian motion at time 0. So this is an identity. This would be distributed like F convoluted with the Gaussian, pushing forward alpha, because alpha is the distribution of that one. And what must happen is that this is equal to mu. Okay. So that's the magic. So alpha has to be tuned in such a way that when you do this diagram, this curious looking object is exactly mu. There is a shorter way to write this, namely your gradient of a convex function is pushing forward the convolution of alpha and the Gaussian into nu, and the convolution of F with your Gaussian pushes forward alpha into mu. And let's call that the Bass system. And so what's written here is that under the connectivity assumption, there exists a solution to the Bass system. And this is rather non-trivial. Yeah? So we like these martingales a lot because they have, if you think about how would you change Brownian motion just to meet the marginal distributions mu and nu, the best case scenario would be, well, at every time I perturb it a bit, maybe with the gradient of a convex function, and this is achieved precisely by these Bass martingales. So it's a bit of a miracle that they exist. And there are no regularity conditions, just this connectivity assumption, all right? If anyone has a question, just go ahead. Yeah. Yes, every Bass martingale would satisfy the connectivity assumption. Brownian motion explores all the available space, and for that reason, the Bas Martingales too. So it turns out this is not just a sufficient condition, it's completely necessary and sufficient. I will not go into the proof. I will just tell you, the key is duality, and this also allows us to get the if and only if, that you're asking for, Benjamin. As in classical OT, it's better to pass to maximal covariance than Wasserstein 2. So maximal covariance is just the sup of the inner product over all couplings, with the marginals mu1, mu2, let's say. Okay. So here we profit from the fact that we know that the continuous time problem is equivalent to the one-step problem. The one-step problem looked exactly like this, but here we have Wasserstein 2 distance. I am telling you, as in classical OT, you can, except for flipping sign or something like this, you can pass to maximal covariance. So I hope this is believable. And yeah, what we show, if we now call this our original primal problem, is that it admits this dual problem. As I said, the superscript star means convex conjugate, and otherwise it's convolution. And this is a very nice fact, but what's more important is that we can show that the dual problem is attained if and only if the primal problem has a Bas martingale as its optimizer, and if and only if the previous connectivity condition holds. So everything fits together, and this is where all the work is into showing this equivalence. Okay, but as I said, so then the main point is that it's a little miracle that this system has a solution, and we know it has a solution if and only if this connectivity assumption holds. And this relates a lot with works from, for instance, from Yonghang and Nasir Gusub, also Nizar Tusi, so on, because when this does not hold, what you can try to do is, I try to partition the space into parts where this would hold in the locally. Then if you manage to do that, then you can also do this locally. So in each of those parts, you would apply this theorem. Okay. So essentially, this really characterizes the solution of the problem, even beyond the connectivity assumption, because you can do this partition of the space. Okay. So an invitation, I think, in general in Martingale OT, but also in our problem, not much has been done about computational aspects. Doesn't mean that nothing has been done. There are some works, but certainly not at the level of development as classical OT. So for instance, here are a few questions. So how could you determine the connectivity assumptions sort of computationally? It is known by works of, by the way, Matthias, Benjamin, Gudmund Pama, William Margheriti, that if you move around the data, perturb the data, you can have instability. You have instabilities in dimension bigger than 1, but not in dimension 1. But could it be that in higher dimensions, if you add some more structural assumptions, you recover stability in particular cases? This is not done. In terms of how to compute these Bas martingales, these iterations have been proposed by these authors, and the convergence and the convergence speed of them has been established by the group of Bea, also Gudmund Pama, Marini. So these iterations are very natural if you go to the picture. So say you have a candidate alpha, you go here, alpha convoluted with Gaussian. For sure, you can find a Brenier map that takes you to nu. Now you take expectations, well, you might or might not get here to be equal to mu. If you can, what you can always do, even if you're not equal to mu, is to take the inverse of that one, apply to mu. That would give you a new candidate alpha, and you iterate. So that's these fixed point iterations that have been proposed and studied. And you have concrete formulas for all of this. Yeah, I didn't say it because I don't want to overextend it, but everything is pretty neatly connected. So that's the reason why I put here gradient of phi star. So actually, if you would have the solution to the dual problem, you call that, psi, the solution, then psi star would be precisely this Bernoulli map and so on. So you have formulas for many of the ingredients, as is the case in these iterations. Yeah, can you solve these problems? The dual problem, for instance, the group of Gregoire-Lepere, they're usually trying to tackle the dual problem with their PDE's perspective. Does it help to regularize the problem? I really don't know. So a lot of things that people could try to contribute. In the last few minutes, I will present a connection to something that looks different at first sight. That was a bit of a surprise to us. So we have our problem of, our primal dual problem. They have the equal value. And now we introduce this functional. It's just a functional of the alpha in the picture. Yeah. And it compares alpha to mu and the convolution alpha with gamma to nu. Okay. So it's comparing these two and these two in the sense of maximal covariance. Okay. We knew that this functional had something to do with our problem because if you try to find a critical point for this one, you write down the system and you get the bus system. So alpha is a critical point if and only if alpha fulfills the bus system with the corresponding f. So we knew that it had to have something to do with us. But what we showed later, or more recently, is that minimizing this so-called bus functional gives you exactly the same value of the problem. And the optimal alpha is the one that works for the bus martingale. Yeah, I think I don't want to, if someone asks, this is a heuristic why this is the case. And the final slide, I want to say, this is not a proper attempt at a computational approach that we have, but it's maybe the start for that. So we wanted to say, okay, we need to minimize alpha in all the bus functional in order to solve our problem. So maybe the one thing you could do is try to do a gradient flow in order to minimize this functional. For instance, in dimension 1, this one is convex in the sense of the displacement interpolations. So maybe to minimize this one, you could try to follow a gradient flow. And I'm sparing you the details, so you can do that. You can do the gradient flow. Something that worked for us was, instead of working with alpha and as a measure, we realized alpha as the law of a random variable. We fixed the probability space containing these random variables. So we translate everything in terms of an L2 space. So what people call the Lyon's lift. And we do then a classical gradient flow, Hilbert space gradient flow for the L2 space as our Hilbert space. And it turns out that these are the dynamics of this gradient flow. It's a bit nasty. What's written here is the Brenier map from this measure in the subindex to this measure in the superindex. So interestingly, under the conditions that we need for this to converge to the minimizer, you also get for free the exponential rate. But this is in dimension 1 to get the exponential rates. If you drop exponential rates, all of the other statements are true in general dimensions. So I would hope that someone could sort of maybe implement this somehow, but probably ambitious given the form of this, yeah, but it would give another method than the iterations that I described. All right. Thank you for your attention.